Welcome to the Bad Mofo Show. I am your host, Bad Mofogarty, and it's been a while since my last video release. Over a year, I think. Long story short, when I started this video series, I had also started a new job, and my free time landed on some odd hours of the day, so it made it difficult for content creation. But recently, another creator commented that it was a shame for someone to have nice equipment and not do anything with it, and that kind of lit a fire in the back seat. So all excuses aside, and with renewed vigor and enthusiasm, let's jump into today's episode. In today's world, the very important subject of resistance and resistors. To start this discussion, we need to revisit a facet of last episode when I talked about electricity needing a path in which to flow. That path is a conductor. The ease in which electric current flows through any given material is known as its conductance, and conductance is the quantitative reciprocal of resistance. Resistance is the opposition to current flow in a material, and most materials resist the flow of electric current to some degree. Good conductors, like metals, tend to have a low resistance and high conductance, while poor conductors, like rubber, tend to have a high resistance and low conductance. There are also materials called superconductors which exhibit zero resistance, but that's for another video. Instead, let's talk about the man who discovered the proportionality between voltage applied across a conductor and the resultant electric current. George Simon Ohm was born in 1789 in Erlangen, a city then part of the Holy Roman Empire. It exists in what is now Bavaria in Germany. His father, Wolfgang, was a self-taught locksmith, and although not formally educated, Wolfgang was able to educate himself to a high level and was well respected. Thus, he was able to instill in George a high standard of mathematics, physics, chemistry, and philosophy. This was apparent, for in 1827, while working at the Jesuit Gymnasium of Cologne as a mathematics and physics professor, George published Die galvanische Kette mathematisch bearbeitet, or the galvanic circuit investigated mathematically. Arguably his most important work, Ohm described in it his complete theory of electricity, and in that description is the first appearance of what we know today as Ohm's Law. Although this work has greatly influenced the theory and applications of current electricity, it was not well received. The college was unimpressed, and George resigned his position. In 1833, he applied for work at the Polytechnic School of Nuremberg and was accepted. And in 1852, he became a professor of experimental physics at the University of Munich. Although initially receiving little enthusiasm, George's work was eventually recognized by the Royal Society with its award of the Copley Medal in 1841. He became a foreign member of the Society in 1842, and in 1845 became a full member of the Bavarian Academy of Sciences and Humanities. George Ohm's work became the early beginnings of the subject of circuit theory, though the importance of the field didn't become evident until the end of the century. He died in Munich in 1854 at the age of 65, never knowing that his efforts would be included in the foundations of the study of electricity and electronics as we know them today. His name has been incorporated into the terminology of electrical science and expressed with the Greek letter omega, has been adopted as the SI unit of resistance, the ohm. Let's examine Ohm's law. Generally speaking, Ohm's law describes a relationship between voltage, resistance, and current. I say generally because there are certain qualifiers that affect the precision of this statement, but for most intent, it gets us close enough to prove its own validity. Ohm's law can be expressed in a few different ways, and this representation I found to be the most common. I equals V divided by R, where I represents the current flowing through the conductor, V represents the voltage applied to the conductor, and R represents the resistance of the conductor. Other equivalent expressions can also be used depending on the need to simplify for finding an unknown value in the equation. Another popular expression is this. If you point to the value you wish to know, the expression shows you how to solve for it. If you want to know the voltage, you multiply the current by the resistance. If you want to know the current, you divide the voltage by the resistance. And if you want to know the resistance, you divide the voltage by the current. The algebra here may intimidate some of you, but bear with me. If this is your first brush with the mysterious algebra, the following should prove to be a simple yet effective introduction to it. I also plan on dedicating a series to mathematics, so later on, if you're interested, you'll be able to find more content on the subject there. But for now, let's plug some numbers into this equation. Let's say we have a known voltage, 1 volt to be exact. We also have a conductor with a resistance value of 1 ohm. We'll use Ohm's law to calculate the amount of current that would flow through the conductor. I is equal to V divided by R. So the current equals 1 divided by 1, which is 1. The current is 1 ampere. Amperes are the SI unit of current, officially named after André Marie Ampere in the year 1881. But that's another story. If we step back and wrap our heads around this equation, we see the relationship between voltage, current, and resistance in its simplest form. If 1 volt is applied to a conductor that exhibits 1 ohm of resistance, the resulting current flow will be 1 ampere. Let's say that instead of 1 volt, we apply 12 volts to that same scenario. I is equal to V divided by R, so the current is 12 divided by 1, which is 12. The current is 12 amperes. We can see that for any one given resistance value, the increase in current is proportional to the increase in voltage. What happens when we change the resistance value? Let's say we apply 1 volt to a conductor with 2 ohms of resistance. Again, I is equal to V divided by R, so the current is 1 divided by 2, or 0.5. The current is 0.5 amperes. What if you know the current and the resistance, but not the voltage? We just use Ohm's law again and plug in the values that we know. Let's say our known current is 0.5 amperes and our known resistance is 2 ohms. V is equal to I multiplied by R, so the voltage is 0.5 times 2, which is 1. The voltage is 1 volt. What if we know we are supplying 12 volts and there are 3 amperes of current? R is equal to V divided by I, so the resistance is 12 divided by 3, which is 4. The resistance is 4 ohms. Now, let's talk about resistance as a tool to accomplish tasks. Following the realization of electricity as a useful tool, inventors began looking for ways to use electromagnetism to run machines. Up to that point, machines had been powered by steam, animals, or even humans. The first commercial use of electricity was in electroplating in the mid-1850s. Later came electric motors. As time went on, new advancements were made and electrical tools were refined, and new electronic devices were invented. Enter the resistor. Born in Dallas, Texas in 1920 to a homemaker and carpenter, Otis Boykin began his journey to become a great contributor to the field of electronics. He graduated from Fisk University in 1941 and took up work as a lab assistant. In 1944, he began working for the P.J. Nilsson Research Labs in Illinois and shortly after started his own company, Boykin Fruth Incorporated. From 1946 to 1947, Boykin pursued graduate studies at Illinois Institute of Technology, but had to drop out when his family could no longer afford the tuition. His interest in the up-and-coming field of electronics blossomed despite this setback, and he concentrated on inventing. In 1959, Otis Boykin received his very first patent for a device that would precisely regulate electric current for specific purposes. And thus, the resistor was born. As electronic tools became more sophisticated, many of the components that comprised them were consequently more delicate and sensitive. They required more precise amounts of electric current to make them operate properly, and the resistor provided this control. To date, there have been many advancements in electric current control, and resistors now come in many different shapes, sizes, and types. This includes fixed resistors, such as carbon film, and metal oxide resistors, variable resistors, such as rheostats and potentiometers, resistor network devices, and more. There are also different mounting styles for resistors. In the mid-1950s, through-hole resistors took the place of point-to-point connection technology on many printed circuit boards, and it wasn't until the mid-1980s that surface mount technology began to grow in popularity. Today, I'm just going to use through-hole carbon film resistors to demonstrate basic classification and function. Yeah, he's a tiny bugger. The next item of note is that resistors are made from materials called semiconductors. Sound familiar? In the last video, I talked about conductors and how electricity needs a path in which to flow. Partly borrowed from Latin meaning half, we use the term to describe a conductor that only allows for partial current flow. Depending on the type and amount of semiconductive material used, a resistor can have an ohmic value of virtually any amount. This brings us to the subject of determining the value of resistors. Due to their compact size, surface mount resistors simply use a 2- or 3-digit code to describe their ohmic value. However, carbon composition through-hole resistors are large enough to employ a series of colored bands to describe their ohmic value, as well as tolerance and even temperature coefficients. Virtually all leaded resistors display this color code. The code is defined by the International Electrotechnical Commission, or the IEC, headquartered in Geneva, Switzerland. The color code looks something like this. The colors in order starting from 0 are black, brown, red, orange, yellow, green, blue, violet, gray, and white, with gold and silver representing the tolerance or percentage of error to expect in the resistor's resistance. Resistors can have 3, 4, 5, or even 6 bands, depending on the quality or accuracy of the resistor's ohmic value. Knowing how to read a resistor code can be tricky. First, you need to determine what direction to read from. Usually, the first digit will be the one closest to a lead, and if the color bands include gold or silver, this makes it easy because they are never the first digit and are oftentimes the last. The first 2 digits are always significant digits, meaning that they represent the first 2 numbers in the resistance value. In a 3 or 4 band resistor, the third band serves as the multiplier in powers of 10, and the fourth band represents the tolerance. In a 5 band resistor, the third band represents a third significant digit, while the fourth band represents the multiplier and the fifth band represents the tolerance. A 6 band resistor is just like a 5 band resistor, except its 6th band represents the temperature coefficient, which denotes how much the resistance of the resistor can change with a specified change in temperature in the resistor's operating environment. It can also describe the failure rate in resistors manufactured to military specifications, although these type of resistors are rarely used in commercial electronics. Well folks, unfortunately, due to time constraints on the current platform I'm uploading to, I have to split this video into 2 parts. So join me on part 2 of resistance and resistors, where I put this science to the test and start using digital multimeters and some other neat tools to demonstrate Ohm's Law. Till next time, I'm Mo Fogarty, and I'll see you on the next Bad Mofo Show.